In this video we're going to observe another effect that can cause a nonlinear response, which is that GM often changes during the operation of a common emitter amplifier. You can see a cartoon depicting another nonlinear output from a common emitter amplifier at the bottom of this page. Here the output sine wave looks different on top than on bottom, appearing pinched and probably not reaching the full 0 to peak value that you see at the bottom of the sine wave. We refer to any nonlinear behavior in an amplifier's output as distortion, and common emitter amplifiers are very distortion prone for even modest output swings, so you don't need to clip your transistor by entering another region of operation to see nonlinearity. As a side note, observing this distortion in your results can be subtle. I've trained myself to compare the top and bottom halves of sine waves in any simulations or measurements I take, so that I can start picking up the first whiffs of a distorted signal. So that's a neat trick. Look at the top and look at the bottom. Like last video, we'll make the amplifier a bit more concrete to see why common emitter amplifiers are so distortion prone. Here we presume that IC is 1 milliamp and RC is 4 kilo ohm. This implies that our GM is 40 millisiemens, which we get just by taking IC divided by phi t. And our voltage gain is minus 160, because it's minus GMRC. However, when our output voltage moves around, that's because the instantaneous total signal current is changing. I've captured that by rearranging V out equals VCC minus ICRC to show the instantaneous value of IC that leads to some value of V out. That has a lot of knock-on effects. Changing V out means changing IC, which means that our instantaneous GM is changing as IC goes up and down, which means that our voltage gain is changing. So if AV changes as our output voltage moves around, that'll result in an output wave that looks different than the input wave. Some parts will be amplified more than we'd expect, and some parts will be amplified less. So predicting the exact shape of the wave is involved, but you can get a quick guess at your percent error at any given output voltage by taking the ratio of your gain to the gain you are aiming for, which, if you follow the math through, is the same thing as taking your instantaneous total signal current divided by the large signal current that you presume is always running. This is a big problem with common emitters, which we'll work on fixing in a future lecture series. But you can still use a common emitter amplifier as long as your output is a legitimately small signal. So in summary, our CE gain is minus GMRC, but GM changes with changing collector current, which is equivalently to saying that it changes as Vout changes. This produces distortion, which causes our output to look like misshapen sinusoids, and it's often easy to spot this distortion if the top half of the wave doesn't match the bottom half. And we can calculate our percent distortion at any given current level by taking the instantaneous collector current for a given Vout divided by the large signal collector current.